So this week we're looking at these 5 problems, Calc 2 through Algebra. I believe this is the first question. We did this one last time, the calculus problem last time. So today it's 24 through 28. So anyway, let's get to it. First, let's take a quick look at the questions. Here's a Calc 2 question. It's about work. It's like a water tank that you're pumping water out of. The multivariable one is to find the unit tangent vector. It's not too bad. Diffie-Q, a little bit gory, but a pretty straightforward procedure. It's just separable equations. Linear algebra 1. It looks pretty abstract if you're not familiar with it, but there is like one big theorem that takes care of all of this. So this is also kind of an easy one if you don't have to prove anything. And then the algebra one is pretty straightforward if you know what abelian means. So here we go. This first question we're working on. The cylindrical water tank has a height of 10 meters and a radius of 3. It's full of water, and we're going to pump the water through the top of the tank. How much work is done to do that? So this is in meters. I guess that means our answer is going to be in like Newton meters or joules for the work. So I'll talk about that in a sec, but you would need to know how heavy water is because you're taking the weight of the water. You're basically going to take a bunch of slices and maybe I should leave this up. I don't think anyone can read that. Let's see what I can do. Yeah, maybe I can just leave that up for you. So that's the question. And we're so yeah, cylindrical water tank. You got the cylinder. It's got a height 10 meters and a radius of 3. Looking at this from the side, take a height y, and then what you're doing is you take a little slice of this thing and turn it into a volume. So suppose it has like a thickness dy. Then the volume that you've got, the volume of water of this one particular slice, is something like pi r squared dy. In our case, it's 9 pi because the radius is always 3. So 9 pi dy, or 9 pi delta y if you want to call it that. And then you have to move this a certain distance. This slice, if this is a height y, then the distance you're moving is 10 minus y. So we would usually integrate as y goes from 0 to 10. This is the distance. And the force we're integrating is I didn't actually turn it into a force yet. This is a volume, 9 pi dy, right? we're doing something like work is force times distance. And we're doing that for a bunch of slices and we're adding them up. Of course, we're actually taking the limit of those, as the slices get thinner and thinner, so it becomes an integral. But that's the concept, is you're integrating, you're summing up work over a bunch of pieces. So this last comment comes in handy right now. This is in cubic meters. And so I need to turn this into a force. So there should be some other term here which turns this stuff into newtons so that I can get newtons times meters and sum up over it. Anyway, that's going to be, well, there's like 1 kilogram, sorry, I should say there's 1 gram per milliliter. Water's density is 1 gram per milliliter, which is like a kilogram per liter, which is like 1,000 kilograms per cubic meter. Okay, it's a big amount of water, I guess. It's like 2 tons of water in a cubic meter. Anyway, we have this many cubic meters times, so this should be like, it's basically a force density or a weight density of water. And I jotted it down on there. You would get the kilograms, that's this part, and then you'd multiply by the acceleration. So this is mass times gravity to give you a force. And this is still this is density. So this is kilograms per cubic meter. Is that hopefully that makes sense? I'm not going to jot it down, but that's where this number comes from. 9.8 times 1,000 kilograms per cubic meter. So now I've got that number. Let me see, so I think I'm going to get 88,200. This is 88,200 pi times this integral. Anyway, yeah, I don't know if you can see that. So when we integrate this, you get, of course, 10 minus y. It's actually like negative half of that squared, evaluated from 0 to 10. So if you plug in 10, you get 0. When you plug in 0, you get 10 squared. So I think I'm getting 50 on this answer. So 50 times this is 4,410,000. So this chunk was 50 when I integrated it. 50 times 88,200 pi. So final answer is 4,410,000 pi, and that's in joules now. Yeah. Let's move on to 25. This is find the unit tangent vector. So for this one, this is 24. For 25, you sort of have to know, as we're moving around on a surface, over time, this path is in 3D. It's like moving around. So here's our little position. You think of it as like a particle or something moving around. But at every moment, there's a tangent line. Tells you the direction that we're moving. So if this is r, which is a vector valued thing, but I really just think of it as position. If r is given to us by t2 sine of t and 3 cosine of t. This tangent vector is given just by its derivative. Just like in 2 dimensions or even 1 dimension, I suppose, we've got derivatives in 3 different directions. So at this moment you have little derivative vectors going in the x, y, and z directions. So you just take r prime. And then all you do with that is turn it into a unit vector. So you basically just know that this is the definition of a unit tangent vector. That's one of the things you learn early on when you're talking about vector-valued functions. So we take the derivative of this guy, you get 1, 2 cos, and it looks like -3 sine. I'm going to need that guy's magnitude, but it might not, it's not going to be anything really pleasant looking. Its magnitude is root, and then you just sum the squares of these guys. So 1 squared plus 2 cosine squared plus this stuff squared. So -3 squared is 9. Sine squared is sine squared. And these could combine a little bit if you want. Like you could make this, suppose you could pull 5 sine squared out of this and then combine the 2, the 4 cosine squared plus 4 sine squared. If you wanted, you could express this as 1 plus 4 plus 5 sine squared, if you prefer. Either one of these would be the same thing. And so finally, our answer is this by definition. And so we get, well, maybe let me write this out front. You got this part times, and then here's the vector part, r prime. You just write 1, 2 cos, -3 sine. Don't think it's going to play nicely with this denominator, so I would probably leave it like that. Or you can write ijk to get rid of these brackets if you prefer that notation. And that's it for the multivariable one. That's a quick one. I'm sure they'll get worse. We're still kind of early in the problem sets, so that's why they're still doable. That's why I'm still having a decent time solving them. 26 says, it's a differential equations question. Find the general solution to this. We've got y prime is 4y plus 3 cubed over t to the half. We're getting lucky here because this is separable, meaning you can divide by a function of y, and all that's left on the right hand side will be stuff that depends only on t. You separate. I usually put the dt on the right just because, I don't know, I like seeing it over there. It gives you the same thing. Now we're going to integrate both sides. This is a power rule. So if you add 1 to this power, you'll get t to the half. You want to also divide by half. So there's that. And then you usually put the plus c on the right hand side like that. You put the plus c with the t part. On the left, we have to integrate this stuff. I guess I could do it super quick, but I got time. Maybe I'll just do it slowly. You could do a u substitution. You let u be this inside stuff, and then you take the derivative of u. In this case, that's 4. And so that tells you how to replace the dy part. This is a quarter du. So this integral is the same as u to the -3, but then I'll replace dy with a quarter of du, like du divided by 4. So there's a quarter popping out. And then when you actually integrate this, you do the same thing. It's another power rule. You add 1 to this, and you divide by that new power. And you don't need to put the plus c over here. In a sense, there's a plus c on both sides, but you just put them all on one side. Now I should put it back in terms of u of y. So this is this formula again, but instead of u, we're going to write 4y plus 3. And we're not nearly done. Well, all you do here is solve for y. We've done the calc part. Now you're just doing a lot of hideous algebra. So multiply by -8 on both sides. It looks like you'll get -16 root t. And I guess it's -8c, but no one cares about that. It's just some constant. It's going to be there in our answer at the end. So if you're feeling crazy about this, maybe put C prime or C2 or something, but nobody ever does that. You just keep calling it C the whole time, even though we understand it's a multiple of the old C, but no one cares about the old C. So some constant is sitting there. All I did was scale by 8, so now we're still here. And you want to solve for y, so take the reciprocal. Flip this upside down. Take 1 over both sides, and you'll get 4y plus 3 squared is 1 over this mess. And now take a square root and subtract. We're pretty much done, right? Subtract 3, divide by 4. So this hideous square root creature. Yeah, there's y. This hideous thing, subtract 3 from all of it, and then divide by 4. We're pretty much done with this problem. Y is a quarter of, well, you subtract 3. I'll just distribute the quarter in a sec. Subtract 3 from this mess. Got double square root action going on here. Isn't that weird? Subtract 3 from everything, and then still divide by 4. So it sort of works out to be that at the end. This is our final answer on this. It's all right. I got 2 more problems here. It's going to do this linear algebra question and this abstract algebra question. The linear algebra looks kind of crazy if you haven't seen this stuff before. It says T is a linear transformation. That basically at this point means it's a matrix. It's an n by n square matrix apparently because it maps from Rn to Rn. But anyway, it tells you that you have some linear transformation that does the following. It fixes, well, it doesn't fix the point, but it maps one vector to the same thing. Sorry, it maps 2 different vectors to the same thing. Can it be an onto map? Why or why not? There's this giant theorem in, well, this is the short version of it, but there's this big theorem in linear algebra about what it means for a map to be onto and invertible. Like if it's invertible, then it's onto automatically in this case. But this is not going to be invertible. What I mean is, like, if you told me what's the inverse or what's the pre-image of T of U, you don't know whether to tell me U or V because it gives you the same image. It gives you the same result for T. So this would not be an invertible function in the old, in the regular function sense with like one real variable. If you had like f of 1 equals f of 2, and someone asked what's the inverse of f of 1, you wouldn't know whether to tell me 1 or 2, or maybe other things, I don't know. So f is not invertible. I'm just daydreaming here, just thinking about how it would be with regular functions. So it looks sort of like you have this kind of situation, right? If you had like y equals x squared, and someone says, well, how do you get 4? Well, you have 2 different answers for that. You don't have one answer, which is why you say this is not an invertible function. You could restrict it to only positive answers if you want, only positive inputs, and then, yeah, that's invertible. But anyway, so that's what's going on here is we've got something that you can't invert. This is not an invertible transformation. So a quick answer for this is, can it map onto? They're saying specifically onto, meaning it covers all of the space. The answer is no. You can be kind of lazy with this one. You can just say, well, it's not invertible, and we know some from this fancy theorem. In fact, let me see if I can pull up exactly that. Invertible matrix theorem. Well, sure. Yeah, here's what I'm talking about. See this big, generally in these linear algebra books, there's a big theorem that tells you the same thing again and again. Like, if you can solve the system, well, here, we'll have a little system conversation. If you had an equation like this, and then you have just the same equation again, well, you don't really have two different equations, do you? You may as well have just told me 0 equals 0 for the second one. So this is an example of a system where it's a system where you can't, when you go to row reduce this, you'll just get a line of zeros. And so this is not invertible. Like this matrix has 0 for a determinant, and you can't solve the system. I mean, at least not in general. You can't get one. It's not solvable. So that's what's happening here is we've got a system, I guess it doesn't say it right here, but the matrix is not invertible. It's not one-to-one, which also means, by the way, it's not onto. So if you want to answer this just by saying no, not invertible, period, end of discussion, that's fine. Another way to think about this is if you made a basis for Rn, if you said Rn is the span of like this vector, which is non-zero, and a bunch of other stuff, when you go to apply t to this space, it's not going to actually give you back Rn. It like collapses this first vector. So there's no way it could be onto, because even though this is Rn, when it acts on this space, it loses a vector. It's the dimension of t is basically n minus 1 instead of n. So it's not onto. Oh, take care. Yeah, the other thing I was going to say, yeah, this was probably a better explanation. If you don't know like any theory, you could say something like this thing that I was just talking about with the span. You could say, well, I noticed that it like annihilated a non-zero vector, which is abnormal. So if I made a basis for Rn that contained that vector, apparently your linear transformation like doesn't even give you the same dimension. It doesn't even preserve the dimension on that space. So there's no way that it could be onto, because it, here's the image of Rn, and it's not Rn anymore. It's apparently Rn minus 1. So that's another explanation. Or you could just quote the rank nullity theorem. You're supposed to have full rank. T does not have full rank, apparently. The nullity of T appears to be, well, I guess I don't know that it's 1. I was going to say it's 1 because it's killing off this one vector. But it didn't say that that's the only vector that it kills off. Oh, wait. Yeah. So like right now, all we know is that it does kill this vector off. I suppose it could be possible if there's a distinct other pair. It might also be equal to T of W, right? And then they just didn't mention it. So never mind. I was going to say you could use this. You can still use this because clearly the rank is not full rank because the nullity is greater than 0. I can say that much. Normally you would want nullity to be 0. The dimension of the kernel, meaning like the dimension of the set that T annihilates, T turns into 0, we can see that it's at least 1, which is already enough to stop talking about this and say, nope, it's not an onto linear map. So this question is like a lot of linear algebra questions. It sounds really scary if you're not familiar with a theorem or two, but it's really not bad. It's really easy if you rely on a theorem, which you probably should do. All right, moving on. This will be the last one for today. I posted this question this morning at midnight, so I probably should maybe wait, but I don't know. I like to do everything on Fridays. This is 28, and it says by a billion I mean that it's commutative. It means that every element in the group, so let's say A and B are elements in the group G, just general elements. If they all do this, for all A and B in your group, then it's a billion. So yeah, fancy way of saying that everything in the group commutes. So the question is, this is an early one from, actually let's click on it. I'm going basically week by week. So this was chapter 1 of Saracino. These questions are coming. I mean, if you check the notes, I have references at the bottom. So I generally stole all these homework questions from here, and I'm just posting them, and then I'm going back and doing them. So the algebra questions, these are all coming. This is chapter 2 of Saracino. This one's from chapter 3 of Saracino, when he's finally starting to talk about groups. Actually, wait, this one was about groups too, huh? Yeah, this was just basic definitions of groups. This one we're talking about identities and being a billion. Anyway, nice, calm, easy question. This one's actually not bad, right? Suppose you have a group, certainly, and suppose that in that group, whenever you take any element, it is its own inverse. It gives you back, let's say, 1, if we're dealing with multiplication. So let's say if this happens for all x in G, can you prove that this happens? Can you prove that it's a billion? Right? So that would mean that apparently a squared is also 1. Anyway, just try something, try anything. We're looking at this object. So what happens if you square it? If you multiply by itself, you're definitely getting 1. It's associative, so you can regroup this stuff. So it's safe to just write it like this with no, concern about the meaning. It's not like if I group it differently, it'll mean something different. You're not allowed to move the terms, the factors around, but you could do that. You could draw out the parentheses. I'm saying that because if you multiply on the left by A inverse, here, like, if I multiply on the left by A inverse, we're going to end up seeing that A is its own inverse. I realize that's obvious. I kind of just said that, but if you started with A times A is 1, you multiply on the left by A inverse, this of course gives you 1. That's part of the definition of being a group, is that you have inverses. So we just saw that A is its own inverse. So if I multiply on the left by A, I should get A times 1. And it should also cancel over here. So you're getting B is A. And if you multiply on the right by B is its own inverse, you're going to get BA. I'll just do it slowly. I'm multiplying on the right by B inverse. Did I screw that up? Well, B inverse is B, so I don't know why I'm writing it like that. But this cancels is the whole point. You're getting BA times 1 equals AB. And that was what we were trying to prove. So given two elements of G with this property, you sort of immediately get that it's an abelian group. No matter what the other structure is, you know, it doesn't have to be finite or anything crazy. But yeah, I know that's an easy one. If you've taken this abstract algebra course, you could definitely handle that one. So yeah, if you took AB squared, we know that that's 1. We're here, right? And you just multiply on the left by A and the right by B. And you'll get left by A and right by B. You'll get that statement, which is all we wanted to prove. And that is it for today, ladies and gents. Thanks for watching. Have a great day. I will go post these